I want to remind you of three things that we've done over the past several courses. Um, in Calc 2, if we had an integral that looked like this, let's say the integral of the square root of 1 minus x squared dx, that we might do what we call the trig substitution, right? Where we say x equals, maybe I'd say sine theta here, okay? And then I'd have to figure out what dx equals. Dx is equal to cos theta d theta. And then when I make the substitution into the new variable, I have to change the. Actually, let me do this even more. So x is between 0 and 1, let's say. So when I make the substitution, there's three things that I have to do here. One is that I change the function. I change my x's now into theta, so this is 1 minus sine squared theta. I change the dx. The dx becomes cos theta d theta, and then I change my limits of integration as well. So for instance, when x is equal to 0, the sine is also equal, theta is also equal to 0, and when x is equal to 1, I'm talking pi over 2. Okay. So you change the function into your new variable, you change the dx into your new variable, and notice there's that extra thing that popped in there, and you change the limits. Okay. So that's the first thing. And then we had something like this with a double integral over some region. So I might have the integral from 0 to 1, from 0 to the square root of 1 minus x squared. The function I'm integrating is x times y, and this is dy dx. And I say, you know what, I'd much rather do that in polar coordinates. And so I have this change of variables here where x is going, here we go, x is equal to r cos theta, and y is equal to r sine theta, and I make my substitution here, and there's three things I have to do. I got to change the function. This is now r cos theta times r sine theta, not phi. I have to change the dA. The dA for this polar coordinate switch here is r dr d theta. And then I change my limits of integration to match the region. It's still describing the same region, but do it in polar coordinates. So, this region was from 0 to 1 on the x, and 0 to, yeah. So this is like a quarter of a circle here. So my limits are, let's see, I got theta on the outside. So theta is minimum of 0, maximum of pi over 2, and for each value of theta in between, r goes from 0 out to 1. Okay, so we have to change the function, we have to change the dA, and within that there's this extra factor of r that popped in there, and we have to change the limits of integration. Okay. Likewise, we saw the same thing for triple integrals. When we switched to either cylindrical or spherical coordinates, we changed function, we change the dv, and we change the limits of integration. Okay. What I want to look at this stage of the game is general change of variables. So if you've got, let's say, a double integral of some function of, come on now, some function of x and y dA over some region D, not just polar coordinates, we can make essentially any kind of change. So if I have x is some function of, let's not use the same function. So if I have x, I'm going to just use capital X of some two other variables, let's say u and v, and y is some function of those same two variables, u and v, right? That I want to be able to switch my integral into u's and v's. Well, it's easy enough to just plug in, x equals this function of u and v, and y is that function of u and v, just like we did, in the polar coordinates. We said x was this function of r and theta, and y is that function of r and theta. But then the question is going to be, how do I change the dA, and how do I change my limits of integration? Okay, and this is where we've got to start looking at determinants of things. So here's the situation. You've got a UV coordinate system, and you're translating it into an XY coordinate system. Okay? And the dA that you're calculating is, you're saying, if I take, a little bit of area over here, so I've got a little change in U times a little change in V, so this is a little, let's actually use delta. So a little change in U times a little change in V, all right, I've got that here. It's getting mapped by this. This is a transformation, or a mapping, that takes the UV plane and sticks it on top of the XY plane. And if I look at constant values of U, let's say, they're going to turn into certain curves over here. And I don't know, depending on what these functions are, will determine what those curves look like. I mean, if you think about, for, how did I do this? Constant value, if you pick a value of V and you let U change, you're going to be looking at, if V is a constant, you're going to have X as a function of U and Y as a function of U. That's a set of, that's parametric curves. For each value of V, you've got some curve. Likewise, for each value of U, and you let V change, then you're going to have some other set of curves. Right? For each value, you get a curve. Right? For each value of U, you get a curve in the V direction. For each value of V, you get a curve in the U direction. And so this grid over here gets translated into some sort of skewed grid over there. And what we need to figure out is, what are the areas of these little pieces. Right? When we did polar coordinates, those little pieces looked like, they looked like wedges. When we were up here, the theta equals a constant looked like, lines going like this. R equals a constant looked like lines going this way. Or circles going that way, and we found the little area element as one of those things. So in general, I'm trying to do that here. It's like, well, how do I figure out what that area is? Okay. Well, I'm going to do it using determinants. That is, I'm going to essentially say, these are little parallelograms, and the smaller delta x and delta u and delta v are, the closer these things will be to parallelograms. And so I say, I want an edge here and an edge there, so parallel to that curve and parallel to that curve, and I've got this little parallelogram. So how do I figure out how big that is? Well, I want to look at, so this is a delta x, and this is a delta y. And this curve, I don't remember whether it was u as a constant or v as a constant, but let's just say that this was a constant. If I can write here, constant value of v. So I'm changing u here along that, and then I'm changing u for a different value of v along this curve. And so, and I'm looking at that there, that vector is essentially, well, it's delta x, delta y, but delta x, I claim, is going to be this. It's going to be the partial derivative of x in the direction of u times delta u. Right? The partial derivative of x with respect to u is the rate at which x is changing when u changes. And if you look at that curve, that's what you're doing. You've got a constant value of v, and u is changing. So if you change u by just a little bit, then x is going to change by some amount, right? Because x is a function of u. And so you're going to say, what's the rate of change of x in the u direction times the amount of change of u that you made. Likewise, delta y for this vector is going to be the rate of change of y with respect to u times that change in u. As you move along this curve, you're changing just u. V is a constant. You're moving along here in the uv plane. Okay? So that corresponds to this vector. So we'll call that v sub u. All right, that's a vector in the u direction. Now let's look at the vector. Oh, I'm using u's and v's. I have another name for vector. Well, it's capital V. Let's make it a little taller. Right. So then I got a vector going in this direction, which I'm going to call capital V sub V. Right. And how do I get that? Well, it's the same kind of thing. You're going to have a change in x. You're going to have a change in y. The change in x now is because you're moving along this curve, and this curve is going to have, instead of v being a constant, it's going to be u have a constant, then you're changing just the variable v. So that vector over there is similarly going to be a delta x, delta y, but this time the delta x is coming because, sorry, you're taking a partial derivative of x with respect to v and then saying, but I'm changing v by a little bit. All right, so I'm going to move this way along this one. So keeping u constant, I'm only changing v. X is going to change because there's a rate of change in that direction times the amount that you move. Right? Likewise, the y is changing because y is a function of v, and there's a rate of change of y with respect to v, and then you multiply by how far you go in the v direction. Okay. So those two vectors, which I'm calling vector sub u and vector sub v, those are vectors that are parallel to the curves at that point there, u comma v. Right? And it may be different for different values of u and v. They may, the area of each one of these little parallelograms may not be the same, just like in polar coordinates, right? These weren't all the same, depending on where you were. Okay? But now that I have this, I need to find the area of that parallelogram. Well, from the last video, we saw that area is a determinant. So the area is the determinant of these two vectors. So I've got partial x with respect to u times delta u, partial of y with respect to u, delta u, partial of x with respect to v, delta v, times the partial of y with respect to v, delta v. And when you do that, you get this minus that. So partial x, partial u, times partial y, partial v. I'm going to factor out this delta u, delta v, because there's going to be in both terms. I got it here, I've got it there. So it's going to be a whole thing times delta u, delta v. And then minus partial x, partial v, partial y, partial u. And there we go. Right. That's the area of one of those little things, and if you take the limit as delta u and delta v go to 0, they just turn into du and dv. This right here is this matrix, this determinant without the u's and v's in it, and it's what's called the Jacobian. It's the determinant of the matrix that's just got all the partial derivatives, partial x with respect to u, partial x with respect to v, partial y with respect to u, partial y with respect to v. And that is the change of area element. The dA turns into the Jacobian times du dv.